All right, 2.2. We're going to kind of go through the beginning of 2.2 kind of quickly because it completely mirrors what we'd learned yesterday. And so you have all of this in your notes. Looks familiar, doesn't it? I mean, doesn't that look like the notes I handed you yesterday? So why am I putting this up here again? It's actually a little bit different. If you look closely, the difference between what you had on your sheet yesterday and what we have today is what x is approaching. Yesterday, x was approaching some number, 5. 2, -4. Today, it's approaching infinity or negative infinity. So all the way to the right or all the way to the left. And what is our graph doing as we head that way? What you're going to notice is we're going to see the same 6 properties that I put up there yesterday don't change. Nothing is any different than the properties we saw when it was approaching a number. So that's why I didn't have you rewrite these, is you can probably just make a note for yourself because you already have all these properties. So just a reminder, if we have the sum of 2 functions, I can do the limit of each one individually, add the results. Same thing with our difference. Limit of each one individually, add the results, or subtract the results. I do want to point out, you guys have seen this before. Again, back in pre-calc, you had a different way of calling it. Besides a limit at infinity, it was called end behavior. Remember that phrase from last year, end behavior? That's exactly what this is. It's end behavior of our function. As we go all the way to the right, where's our function headed? Okay, so same rules again that we saw yesterday. Product rule, if I were to have 2 functions being multiplied together, I can do the limit of each one individually, multiply the results. Same thing with division. Again, just being cautious that we're not dividing by a 0, obviously, and then we would have to look at other options if that's the case. Constant multiplier, I can do the limit of the function and then multiply by the constant multiplier. And then our last one is our power rule. Again, I can take the limit of the function and then raise the result to whatever that exponent is. None of those rules change. We can continue to apply even though we're headed towards infinities. So let's go ahead and try one, and I'm going to move where this is at because that's kind of misleading. We're going to do the limit as x approaches infinity, and this is the function we're going to look at. So just giving you a little way to manipulate again, and we've been doing this quite a bit, so kind of getting used to this. If I look at this, my function is x plus e to the negative x over x. And I'm supposed to look at the limit as x approaches infinity, or we go all the way to the right. What is this function going to do? You guys have a couple options. If I were to kind of write all that together so it's not like directions and functions separately, as x approaches infinity, one of the things I could do is take the limit of the numerator, the limit of the denominator, and divide. One of the other things I could do is break that into 2 functions. Remember how we broke our fraction, giving both the common denominator yesterday? And I can do that and then do the limit of each one individually and add the results. So it's kind of a personal preference. Both are fine. I'm going to go ahead and break the fraction for us. So I'm going to break the fraction giving both of them that common denominator of x, right? So I can do that, pull apart. And then a couple notation comments I would make on this. First of all, I would never write something as x over x, right? X over x is just 1. So I would rewrite that x as 1. And the second part is this, and you don't have to do this, but if back in algebra or whatever, I had handed you something that had a negative exponent, do you remember what strategy you used to get rid of the negative on that exponent? Put it in the denominator, right? We moved it. And I'm going to move it, and it's going to just kind of support our case a little bit more here. So I'm going to drop that down to the denominator. And remember, e is just some number, 2 point something, being raised to an exponent. So once I raise 2 point something to an exponent, it's going to get bigger, right? As I put bigger numbers in there, if I square it, raise it to the 4th, whatever. All right, so let's talk about doing the limit of each of those terms then individually. Because we're looking at 2 functions, right? Our first function is 1. And the limit as x approaches infinity of 1, is 1 going to change? No. We're going to get that officially in our notes here one of these days, but constants don't change. It doesn't matter what your limit is approaching. A constant stays a constant, hence the name constant, right? It's not going to change. Our other function will, as I plug different x values in. So let's think about what's happening. X approaching infinity means I'm plugging bigger and bigger numbers in, right? So I plug in 10, I plug in 100, I plug in 1,000, I plug in 1,000,000, and continue to get bigger and bigger. So if I plug in 10, I'm talking about 1 over 10 times e to the 10th. This number is pretty big right now, right? And then I plug in 100, and this number gets really big. 100 times e to the 100th, and then I plug in 1,000,000, and this is 1,000,000 times e to the 1,000,000th. That's a really big number, isn't it? But it's in the bottom of my fraction. So if we consider that number like 1,000,000, 1 over 1,000,000. If I told you I was going to give you 1 over 1,000,000 or 1/1,000,000th of a pizza, I just basically gave you nothing, right? If I give you 1/1,000,000th of a pizza, I gave you nothing. So as this number gets really big, this is essentially becoming 0. And that is going to be our limit. That's what limit means. What are we approaching? We are approaching 0 as I plug in bigger and bigger numbers. So then we get 1 plus 0, or 1. You're going to look for that in fractions. In the fractions, you really got to slow down and say, okay, is the top getting bigger faster, or is the bottom getting bigger faster? Because if the top's getting bigger faster, it's just becoming a big number, right? If the bottom's getting faster, it's becoming 0. And that's the difference between where your bigger variable is. Okay? Go ahead and try this one. I want you just to do the positive infinity part of it. And you can work with your table on this, but just the positive infinity. Limit as x approaches infinity. And your function you're looking at is 5x plus sine x over x. All right, we'll see how we did in here. I think when I did this problem second hour, I tricked 100% of the people in the room. I don't know if that's good or bad. Does this look like what we did here to start with? Yeah? Beautiful. And we probably simplified that, hopefully, right? 5x over x, 5. Beautiful. All right. Limit of 5 as x approaches infinity is, this is not the trick part, 5. Okay? Trick part. Limit of sine of x over x as x approaches infinity is, oh, I didn't trick everybody. It is 0. A lot of us went back to what we had been doing, and that was where we were approaching 0. It went up to 1. As we approach infinity, it flatlines at 0. So as we are approaching infinity, sine of x over x is going to go to 0. Now use that whole idea that we just talked about on the last page. Sine of some number can only get as big as 1 and as low as -1, and it's going to keep going back and forth between those two numbers, right? You know your sine graph. And I'm dividing it by a number that just continues to get bigger and bigger and bigger and bigger. So this is at most 1 divided by something huge is going to go to essentially 0. Okay, so then 5 plus 0 is obviously 5. Or you can go back to that graph I gave you, which I'm going to do a terrible job of drawing right now, but it looked something like this, right? Flatlining out here at 0. Questions on that? All right. We were supposed to do a second part to this. Limit as x approaches -infinity. Will that impact our answer? Sometimes. Okay. Does it impact our answer on this one? Well, if I put in a negative infinity here, first of all, is 5 going to change? Still 5, right? Still constant. Is this going to change as I start plugging in bigger and bigger negative numbers or smaller and smaller negative numbers? No, it's still going to essentially become 0 or flatline at 0. So actually, that is the answer to both of our questions, the right-hand limit and the left-hand limit. Questions? All right. Related to each other is this concept of horizontal asymptotes. If we have a horizontal asymptote, the line y equals b, b being some number, y equals some number, is a horizontal asymptote of our function if the limit on the right or the limit on the left is a number. Okay, so there are three things that would make it not have a horizontal asymptote. If my limit was infinity, if my limit was negative infinity, or if my limit does not exist. If I were to say one of those for the limits, it doesn't have a horizontal asymptote. But if I answer any other number in this world, we have a horizontal asymptote at that number. When it asks you to describe a horizontal asymptote, you are going to give me the equation of that line. It's a horizontal line, remember, and that will be y equals some number. Okay? Which is listed right here. Y equals some number is your horizontal asymptote. That number will match whatever end behavior we have that was a number. Now, those don't have to be the same. You can have more than one horizontal asymptote in an equation. You can have a different one for the left than you do the right. They can be the same. You can have just one and not the other. Okay? So just know that you can have any of those combinations. But if either of those are ever a number, that's a horizontal asymptote, y equals whatever that number is. So let's look at some examples. Oh yeah, I forgot. Just some things that might tie that together from pre-calc. In pre-calc, you guys did a whole section on rational expressions, and you had to graph them and all that stuff, and part of graphing them was drawing in your horizontal asymptotes. Showing the relationship between that and the limits. You usually referred to those as little over big, big over little, or same as a common phrases that we use in this building as far as talking about rational expressions. That's talking about the biggest exponent on our variable in the numerator and the denominator. So if the biggest exponent is bigger in the bottom, we call it a little over big. There's an example of something that would have that, an x to the 0 over an x to the first. Okay. Big over little has a bigger exponent in the top. And same is exactly what it sounds like. The exponent that's in the top is the same as the exponent in the bottom. So the end behavior, the limits as we head to the right and the left, what's happening? Well, we can kind of think about just plugging in numbers. If I plug in numbers to this one, it's going to get bigger and bigger and bigger in the bottom, which means it's going to flatline at 0, right? We already looked at that. Also going to flatline at 0 as I put bigger and bigger numbers in the bottom that are negative. What did our graph look like for my visual people in here? It looked something like this, right? That should look familiar. The second one, we've got a big over little. In our big over little, the numbers that I'm putting in here, the top's growing faster, which just makes it a bigger and bigger number, right? And if it just continues to get bigger and bigger and bigger, it is going to head to infinity. Now, think about this. If I'm putting bigger and bigger negative numbers in here, when I square it, it's going to become positive. Here it's still negative. It's going to head towards negative infinity. When I graphed that, it had a slant asymptote. Remember those? It looked something like this was a common example, right? And you can see that right-hand side is going to head up forever. That left-hand side is going to head down forever. Your last one is if the top and bottom of my fraction are growing at the same rate. They've got the same exponent. It's going to end up eventually flatlining at the ratio of the leading coefficients. So a picture of something that's flatlining at 3/4 would be something like this. We would have drawn in this little horizontal asymptote. It would have looked something like that, flatlining up there at 3/4. And the limit as we head to the right and the left is the ratio of those leading coefficients. Generically speaking, we'll just call it the ratio. Okay, so tie that to our horizontal asymptotes that we just had on the last page. We have a horizontal asymptote if the limit, as we head to the right or the left, is some number, right? Well, remember 0 is a number, so these would have horizontal asymptotes. Is infinity a number? No. Ratio is going to be some number. So you can see same. Exponent top and bottom are going to have a horizontal asymptote. Little over bigs are going to have horizontal asymptotes. Big over littles are not. Okay, so that's for your rational expressions. This kind of sums that up. Little over big is always going to be at 0. You won't have a horizontal asymptote for that big over little, and same is going to be at your ratio, whatever that ratio is. All right, I'll give you a second on that one. Not all of our problems will be rational expressions, but this kind of helps you think through those a little bit. Otherwise, we might have to just do it individually as we go. For example, this one kind of looks like a rational expression, but we've got like an absolute value going on in there. So let's talk about this. F of x equals 3 absolute value of x over x. Okay. I kind of want to simplify that because I see an x in the top and I see an x in the bottom, right? Obviously, that absolute value's got to have something to do with my problem. But if I think about simplifying that fraction, that rational expression, I would cross off the x's and I would get something like the y equals or f of x equals, cross off the x's 3. What does that kind of a line look like? Horizontal line, right? At 3. Well, obviously, we're going to be a little bit different than that. So we're saying if x is 1, we'd have 1 here and 1 here, and our answer would be 3, and we'd be up here at 3, right? Good horizontal line. But look what happens when we start changing and plugging in negative numbers. What if I were to plug in -1? If I put in a -1 here, that's 3. Put in a -1 here, it's now -3. So can you see on the negative side that that line's going to end up being down at -3 instead of +3? Yeah? Okay. And then what about at 0? What happens when I plug 0 into this function? Undefined, isn't it? I can't plug 0 into this function. How do I show that on my graph? Open dots. I cannot plug 0 in. That is a domain restriction on this one. I would have to put an open dot at 0. So that was step 1, graph that function. Step 2, describe the horizontal asymptotes. When I describe a horizontal asymptote, if I have one, the description will look like this. Y equals a number. And again, I can have more than one of those because I could have one on the right and the left if they're different. And we, again, think through what is the limit as we head to the right, what is the limit as we head to the left. That's how we decide on horizontal asymptotes. So what is our limit as this function goes to the right or heads to positive infinity? So as I trace this to the right, what's our limit? 3, right? It's flatlining at 3. How about when we head to the left? -3, right? Okay, if we have a horizontal asymptote, we would have gotten a number here. We got actually 2 different numbers here, so we have 2 different horizontal asymptotes. So our answer to describe horizontal asymptotes, we have one at y equals 3. We have one at y equals -3. So I think through my limits as we head to the right and the left, and if either one of them is going to tell me a number, that's included as a horizontal asymptote. Questions? If either of them had said does not exist or infinity, it would not add to my list of horizontal asymptotes. We don't have to have a horizontal asymptote. All right, last one. Let's think about this. We're going to do our right and left-hand limit here. Find the limit as x approaches infinity, find the limit as x approaches -infinity, and any horizontal asymptotes. So if either of those happen to have a number answer. And our function this time is sine of 1 over x. Is this problem going to follow those rational function rules or hints that I just gave us a couple slides ago? Not really, because it's also including a trig function up there, right? So we're just going to think through. On that first one, x is approaching infinity, which means I'm plugging bigger and bigger numbers in here. So as I do that, the fraction inside of my sine function is headed towards 0. Okay, well then that means I'm taking the sine of something that is essentially 0. What is the sine of 0? That's your options, 1 and 0, yes. 0, right? Sine of 0 is 0. So this one would head towards 0. How about as we head to negative infinity? Again, remember when I put a negative infinity here, does it really matter that it's negative? Still going to essentially become 0 because the number in the bottom is going to be so big and negative, it doesn't matter. It's going to essentially be 0. And the sine of 0 is still 0. Do we have any horizontal asymptotes? Is 0 a number? Yeah, 0 is a number. And if we get a number answer, that is a horizontal asymptote. So we have a horizontal asymptote at y equals the number we get on either of those. They were the same, so we have 1. It's at y equals 0. Now, is it always going to be that? What if I change the function to cosine? If I change the function to cosine, is this going to stay 0? What's cosine of 0? 1. So it would not stay 0, right? That was dependent on our trig function there. Any questions for me? All right. Your assignment out of the book, page 76, 1 through 7 odd, 21 through 26.